Hi everyone, I'm Dr. Syed Mustafa Safavi, a cybersecurity researcher and academic with a focus on AI, system architecture, and digital security. I'm joined by Sarah Johnson, a tech entrepreneur and strategist working across emerging technologies. In this podcast series, we combine academic insight and real-world practice to explore critical topics in tech and innovation. Whether you're a student, professional, or enthusiast, you'll gain a balanced perspective grounded in both theory and application. Make sure to subscribe, follow, and join us on this journey as we unpack the future of technology, one episode at a time. Welcome, everyone. Today, we're diving into the fascinating world of computer architecture. We're exploring its evolution, from early mechanical computing to the modern designs we see today.
Absolutely. I've always found it so interesting how the physical structures evolved over time. What's the first aspect we should explore?
Let's start by looking at the historical overview. You see, back in the day, there were machines like the 0th generation mechanical devices, then the vacuum tubes of the first generation. That's really the foundation.
Right. And then came the transistor era, making computers smaller and faster. It's almost like they shed weight and became more agile, if that makes any sense.
Exactly. It's like the transition from bulky, clunky machines to sleek, efficient systems. And then we see the magic of the integrated circuit in the 3rd generation, which really changed the game.
I'm curious, though, don't you think calling early computers non-general purpose somewhat underplays their complexity?
Well, that's a valid point. Sure, they were specialized for particular tasks, but the brilliance was in how the ideas evolved incrementally, each generation building on the previous technology, leading to the architecture we study today.
Absolutely.
And speaking of evolution, there's an interesting aspect where computer architecture began to be seen as the physical attributes of a system. It became the interface between hardware and software.
Yes, and that brings us to the learning outcomes. Get to know the hardware components like the CPU, memory, and I/O devices. It's pivotal in understanding how a computer really works.
Precisely. Speaking of the CPU, it's basically the heart of the computer. It's composed of registers, the ALU, and the control unit.
Right. And the ALU, well, it's kind of like the brain's calculator, executing arithmetic and logical operations, yes?
Absolutely. It's like the computer's internal cache register that figures out everything from addition to logical decisions.
Yeah, exactly.
Now, shifting gears to memory. The topic covers the memory hierarchy really well. There's primary memory, which includes registers, cache, and main memory, and then secondary memory like magnetic and optical disks.
Right, and the memory hierarchy is such a clever design. Data is stored in registers for blazing speed, but that's just a tiny capacity. Then there's cache that bridges speed between registers and main memory.
It's like a layered sandwich. The innermost layer quick and ultra accessible. Then the outer layers providing bulk storage, but at slower speeds.
I always think of it as a race. The CPU is like a cheetah that needs the quickest refresh of nutrients, and cache is the snack bar it runs to when it's hungry for data.
That's an awesome analogy. Now, it's interesting we also touch upon different types of computer memory like RAM, ROM, and even the hybrid memories. Each has its own role in the computer's function.
Yeah, and digital data is stored as bits, zeros and ones. It almost sounds so simplistic, yet is the basis of everything.
Exactly. And when we break down the memory components, the registers are tiny but lightning fast, which is why they're integrated directly within the CPU.
Exactly. Speaking of registers, isn't it fascinating that there are general purpose registers and special purpose registers? It clearly shows the design's versatility.
It is, but I sometimes feel that the differences get a bit murky when explaining them to newcomers. They both serve a similar purpose of temporary storage.
I see your point.
Now, Let's pivot to the layout of computer architecture itself. One of the key concepts is the von Neumann architecture. John von Neumann basically proposed that both data and programs are stored in the same memory space, which was revolutionary.
Yeah, that's a classic shift. But isn't that design sometimes criticized for the so-called von Neumann bottleneck? The fact that instructions and data share the same bus could limit speed?
Absolutely, that's a point well raised. While the von Neumann model made early computing possible by simplifying memory architecture, it can indeed create performance constraints. Yet, for its time, it was a breakthrough in unifying storage.
Yeah, that makes perfect sense.
And then there's the Harvard architecture, which, by contrast, separates data and instructions. This is used in many modern microcontrollers.
Right, so the Harvard model can reduce some of those bottlenecks by having parallel, separate pathways for instructions and data access.
Exactly, it's all about optimizing speed and efficiency. Now, looking at modern architectures like x86, SPARC, and PowerPC, there's a lot of diversity. For instance, the x86 architecture, built by Intel and AMD, has evolved from 16-bit and 32-bit designs to the powerful 64-bit systems in use today.
And what's even more interesting is that x86-64 is basically an extension of that same design. It shows how a solid foundation can scale over decades.
Very true. There's also a neat interplay between hardware and software here. Computer architecture serves as the instruction set architecture, which basically is the bridge between what the hardware can do and what the software demands.
Yes, and that interface has been crucial in the rapid advancement of tech. Without it, software would be like an artist without a canvas.
Well said. Plus, the topic also covers input-output devices, which are the peripherals that enable us to interact with our computers. Keyboards, mice, displays, printers, but also machine-readable devices like tapes and sensors.
Exactly. Right. And those I/O interfaces are just as critical. A computer system isn't just about processing data. It's about how quickly and effectively it can get that data in and out.
Absolutely. Now, I think it's interesting to note the evolution overall. We went from machines that were almost like giant calculators, a bit like a steam engine, to the sophisticated microprocessors we have today. It's really an evolution in miniaturization and capability.
Yeah, indeed. I'm always fascinated by how these historical shifts not only change the size of computers, but their entire function and societal impact.
Yes, and that shift affects everything, from how quickly you can send an email to how seamless your video streaming is. This underlying architecture really is the unsung hero of our daily tech use.
For sure. But I wonder sometimes these explanations dive too deep into specifics and might lose the layperson. How do you think we can better relate these concepts without oversimplifying?
That's a fair challenge. I think using everyday analogies works well. Like comparing cache memory to a mini fridge that always stores your favorite snacks right at arm's reach, while the main memory is like your big, full-sized refrigerator.
Yeah, that's a great analogy.
Exactly. And looking at registers, it's like they are your immediate desk drawer, tiny, but you look there first for important tools.
I get that. But isn't it also crucial to highlight that while these analogies work, the technical aspects involve precise trade-offs in speed, capacity, and cost?
Absolutely, you've got a point there. While analogies help convey the gist, actual computer architecture is a delicate balancing act between these factors. It's a realm where every bit truly matters.
Absolutely.
Wrapping up, it's pretty clear that understanding computer architecture is key to grasping how our digital world functions. From the historical evolution, the hardware components like CPUs and memory, right through to modern architectures like x86 and beyond, it's all interconnected in a massive dance of innovation.
Definitely. And it's also a reminder of how far technology has come and where it might head next. Thanks for this really enlightening discussion.
Thanks for joining in. It's been, an amazing deep dive into the structural foundations of computing.